much for coming, and I hope this will be a fun talk. Please feel free to stop and ask questions if you have any in between. I try not to be too technical, because not because I think the audience will not get it, but because I don't understand much of this myself, right? This whole particle physics business, it's a huge field, and there's just so much going on. The reason the title is this is I want to talk about the excitement the God particle created, although we don't like the name, but then how it ties up with the next generation of scientists, especially in the context of Nepal and what we are doing now, what some of our mid to long-term goals are in terms of inspiring the next generation of scientists in Nepal, because here a lot of people are already doing a lot of fantastic work, right? Brian Cox is there, and there's Brian Green and all these big guys like who try to inspire the next generation of scientists in Nepal. We don't have so many, so we try to do a little bit of this and that, and then we try to give you a flavor of the research I do and some of the work we've done in Nepal. So we can get started. This was in December 2014. We were in Sangja. If you don't know where Sangja is, it's a small district about 200 kilometers southwest of Kathmandu. We were in Sangja, and then we were talking about, the big science and, Big Bang and how the universe is expanding and so forth. So we were giving this talk on a Saturday, and this room was full of all these kids from 8th, 9th, 10th grades, and they had all come to hear about, there are scientists coming from Europe, let's go here. And then, they were all excited. And after our talk, one kid, like 8th grader, I think, asks me this question. It's like, if the universe is expanding, then the distance between the sun and the earth must be increasing. That means the earth will receive less and less heat, right? Will that counterbalance global warming, was the question. And I was like, wow, man, that's like for an 8th grader, that's a really, really, logical way of thinking, and he really has the ingredients correct. And I'm like, okay, very good question. When you are in college and are looking for an internship, contact me. Here's my email address. I said that. But yeah, I tried to answer him. Of course, the difference in scales between global warming and cosmological expansion, without being too technical, because I didn't understand it myself back then. But yeah, so we went to Sangja because there was a high school teacher who had come to CERN in the summer of 2014, and his name is Mr. Vishnu Lamsal. You can see him there, taking the picture in front of this showpiece magnet, this superconducting magnet, but it's just a showpiece, it doesn't work. He had come for the science teacher training program that CERN organizes every summer for a team of high school teachers from around the world for about 3 weeks, and the idea there is to try and inspire these teachers so that they take some of the inspiration back and inspire the students in their school. So that is the idea. He had come there, and I think he had a wonderful time, and he invited us back to come to Sangja and see what he will have done in December. So from summer, about 6 months after, we went to Sangja, and we had a lot of fun interacting with the students. There were endless questions. So I do these kind of talks, and I come back feeling inspired myself, right? Because when you're at work and you're, punching away the numbers, taking shifts in the room and all that, it can get a bit dry, and then you go talk to all the kids, and then you hear all their questions, and I don't know if this happens to everybody. For me, I come back feeling more motivated. I'm like, there's somebody who cares, right? So we had a lot of fun. Vishnu Dai was one of the teachers who came, and there was another teacher who had come, who came to CERN in 2015. And we're trying to push this program further, because we do believe that if we train high school teachers now, then the effect will be exponential. They inspire more students, and hopefully more students will take up science and engineering, and then that is one way we think is for Nepal to move forward, right? So Kamlesh Chaudhary came from Sinduli. He teaches at Kamala High School in Sinduli. He came in 2015 summer, and then invited us to do a program there. So in December of 2015, we went to Sinduli. Part of the reason we went to Sinduli, besides Kamlesh Dai, is that's my hometown. I'm from Sinduli, and it's like, Kamlesh Dai is from Sinduli, let's go to Sinduli. And that school is right next to my house. And so I'm like, this is close by, and that's where I first learned to do Dui Ekan Dui Dune Char, and that's, there were no classrooms. These buildings were not there, the big ones. We were basically learning to Chaurima and learning to 1, 2, 2, 4 and all that. So compared to back then, this school is ultra modern now. It has all these, these cement buildings, and it has electricity, and there is even a highway, BP highway, if you've heard about it. BP highway runs right beside the school. Although the chemistry lab, as you can see here, is somewhat still primitive, so it's not very fancy school. So we had a lot of fun here as well. You can see this hall was like packed. There were about 120 students, and there were like 30 teachers and staff, and villagers also came there, like, oh, people from Switzerland have come, right? It was not just us, like Abba and I had gone, but there were also, because Abba was working as a CERN communication officer back then, and then we had other friends from CERN who had come, other physicists who had come with us, and they're like, oh, people from Switzerland, all the villagers like came also, so the room is like quite full. And even there, like, you could see there's just so much enthusiasm and talent among the kids in Nepal. Even school, they were asking all kinds of questions, right? And they have all these curiosities, things that would not make sense and didn't make sense to me either when I was growing up. Things like, oh, how did the universe start? What was before the Big Bang? Or the difference between astrology and astronomy, and astronomy or astrology and weather forecast. And kids were asking questions that didn't make sense to them, and so they were just like hungry for knowledge. And we don't have enough teachers who are trained to answer these kind of questions. The teachers basically say, oh, this is written in the book, this is true, kind of thing, right? There's just so much, and well, that's my opinion, so let's not go into that, because pedagogy is a whole different subject, and you can argue about it forever, like the ways to test and all. But okay, so the third teacher that we've had at CERN is Monisha. So you can see her set there in front of the same magnet where we all like to take pictures, because it shows clearly, oh, here is a big accelerating magnet. But Monisha came in 2017 summer. She's part of the, she is a member of the Nepal Astronomy Society, and then she does a lot of outreach programs, a lot of training of high school teachers. So she had come in 2017, and she's now gone back and does a lot of wonderful outreach events, stargazing activities, and training students to use telescope and so forth. The other person standing there is Vivek Pandit. He's an undergrad at MIT, and he came not through CERN summer student program, but through MIT's RU program. So we're all together there. So, and the reason I'm showing this picture is that's the only picture I could find of Monisha. I wanted to talk about high school teacher, but that's the only picture I have of Monisha. And the other student there is Darshan Talise. He's a senior at UT Arlington. He came through CERN summer student program, and CERN summer student program is the program where CERN basically brings together students from all over the world for about 8 to 10 weeks, and then assigns them a project with a supervisor. So I didn't work with either of these guys. I worked with other summer students, but Darshan is now going to grad school. He has several PhD offers. He has not decided yet because there's just so many offers. So it was a very good student, basically. The fourth guy in that picture, not very important, we won't talk about him. But the other summer students who have come from the reason I'm talking about these summer students is so we train high school teachers. They go and talk to high school students, hopefully inspire them. But then we also have to train students to actually do science, right? And CERN summer student program is that kind of program where they actually come and they don't always publish papers, because in 2 months it's a little difficult to actually complete a project and publish. But then they contribute something to the paper that will eventually be published, right? So when I take a summer student, I work with them for 8 weeks, and I try to create a project that's that small part of a bigger paper. So it's like, oh, compute this number, and then make boxes like you will do this, and then you compute this number, and then hopefully that makes sense to them in a bigger perspective of the paper. So they learn, I think they learn how a paper is written, how a research is done, and how, like, in today's global collaboration, how you contribute a little bit. You don't do like everything to, when we discovered the Higgs boson, there were 3,000 people who were authors on that paper, right? So it's a real global effort, and then they hopefully get a sense of that when they come and work at CERN. That's the idea. So there is Ishan. Ishan came in 2013. Is now a PhD student at Göttingen, working on the Atlas experiment on which I work. Mahesh came in 2016. He's now finishing his master's thesis at Tribhuvan University, and is ready to apply for PhD programs. abroad, obviously, because there is no PhD program in particle physics in Nepal. The other students that we've had at CERN are Yadav Kandel on the left there. So they're taking a picture outside an office where the WWW was invented. So Tim Berners-Lee invented WWW in these hallways, which is downstairs from my office. And then these guys were like, okay, let's take a picture here. But we met all these students during our outreach program. So remember when we went to Sangja, when we went to Sinduli, we'd always do these programs either at KU or TU, where we'd go do lectures in the morning to the university students, and then we'd do a hands-on session in the afternoon or the next day where they actually analyze the LHC data with a user-friendly interface, and then they would actually compute some numbers. And so there, you would identify some really talented students, encourage everybody to apply, and then CERN selects these students to come over, right? And so Yadav was one of them, although he went to ICTP, which is International Center for Theoretical Physics in Trieste, Italy, but he had come to CERN to visit us because he was so close by. And now he's a PhD student at Rochester.
So I have a quick question. Sorry to interrupt.
Oh, no
so
problem.
How are these students funded? Is it by the CERN?
Yes, CERN funds them.
CERN funds.
So normally for the summer student program, they only take students from member states. There are 22 member states in Europe and one in Israel, and now India and Pakistan are associate members. So they take money from these member states, and this money is used to fund summer students and all. But US has its own program through which it sends American students. For Nepal and Palestine and other countries, then CERN has this show of goodwill and takes students from these countries, and so fully funded. And the last summer student I want to talk about is Santosh Parajuli. So he came in 2015, worked with me for 8 weeks, and then he was like, he really loved it. And he was like, oh, can I do my master's thesis working on the Atlas experiment? And we're like, well, Tribhuvan University is not really a member institute. It's not part of the collaboration. It's a little difficult to do. But he was persistent and determined, so we approached ICTP, which ICTP is a member institute of the Atlas experiment. And so ICTP said, okay, ICTP promotes a lot of or funds and promotes basic science in developing countries. ICTP was founded by Abdus Salam, who won the Nobel Prize in 1970s or 80s for particle physics, of course. And ICTP just does fund like a lot of programs in developing countries, and they're like, yeah, okay, so we will provide you affiliation, but you have to work on your own. So because Santosh had already worked with me and he knew what the tools were during the summer, when he went back, we created a project for him to do his master's thesis on. So I was meeting with him on Skype and in email, sending instructions in email, and he basically completed his thesis. Now he's a PhD student at UT Dallas working on the Atlas experiment, but his master's thesis was searching for Higgs. And you may ask, what on earth is Higgs? But I guess first we have to ask, what is Higgs? And even before that, we may ask, who is Higgs? So if you go to the next slide, it said, I found Higgs in 2012 in Scotland. And I was in a summer school there, and Peter Higgs was just hanging around, checking out our posters. And I'm like, oh, Peter Higgs, let's take a picture with Peter Higgs. I was so excited because, we had just discovered the Higgs boson at the LHC, and then there was Peter Higgs. So this was very exciting time. So that is Peter Higgs. So after I met him in 2012, in 2013, he goes to Stockholm. He takes the Nobel Prize. We get no invitation. But yes, there is Peter Higgs. What they had done was they had discovered this theoretical mechanism that would contribute to our understanding of let's say, how the particles get masses, right? And that's an animation. I don't know if you guys wanna. What that shows, that animation is, we had to take a lot of data before we could say that there is the Higgs signal, and this is the plot. We did not know what the mass of the Higgs boson when we were so this particle was predicted back in the 60s, right? And then the scientists searched for it for a very, very long time. Didn't find it. And there was one physicist by the name of Leon Lederman. he was so frustrated. He's a particle physicist himself, had won the Nobel Prize himself for discovering a kind of neutrino, and he wanted to write a book on particle physics. And of course, in the search for the Higgs boson, and since we had searched for it for so long but not found it, he wanted to call the book The Goddamn Particle. But the publisher would not allow that, and so he ended up calling the book or the particle, the book, The God Particle, and then the name stuck, even though physicists don't always like that name. That's the story. I don't know if this is true, but that's the story I've heard from here and there. So these guys predicted the particle, looked for it for a very long time. So between the prediction and the actual discovery was almost 50 years. And this plot basically shows like we had to take a lot of data, make the background modeling. This falling distribution is basically background, and then the little peak there is where we found the Higgs, and that is the signal we're looking for. Don't worry about it if you don't understand it. It's not important for the rest of the talk. Okay, we can go to the next slide. So what exactly had Peter Higgs and Francois Englert, who won the Nobel Prize, done? To understand that, we have to set things in perspective. So everything that we know of, everything that we see around is basically made up of atoms. We all know that, right? Raise your hand if you disagree. So everything is made up of atoms, and atoms, if you've taken high school science, you would know are made up of nuclei and electrons, right? So there is nucleus, and then the electrons go around. It's a very simple picture, not completely right, but makes sense. So the electrons go around. We try to smash it. I don't know why I'm holding this. This doesn't work. So electrons, no matter how hard we smash it, electrons, we do not find substructure. We don't find anything inside electrons. So we call electron an elementary particle, a fundamental particle that has no substructure. That's an electron. But when we smash protons or neutrons that make up the nucleus, can we go back? Everything works for you. Nothing works for me. Oh, this works. This is great. Yeah, protons and neutrons are made up of even smaller particles called quarks and gluons, right? That we know from experiments. Electrons are fundamental, but as far as we know today, these quarks are elementary particles. We don't know if there are substructure inside quarks. So this is what we mean by doing elementary particle physics. We're studying about the matter that are fundamental, that are elementary, that do not have substructure, and this is our current understanding. Everything is made up of atoms, protons, neutrons, and electrons. Protons, neutrons are further made up of quarks and gluons. So this is everything condensed into one picture. So we have electromagnetic force. Electromagnetic force is mediated by photons, the particle of light that we see. So there are electricity and magnetism combined into one force called electromagnetic force. It's mediated by, so when an electron interacts with a proton, the mediation is done by photons, like particles of light, and there are particles of light that we don't see by our eye, but there is infrared and gamma ray and X-ray and other particles. They're all photons, right? And there is the weak force that is responsible for radioactive decay, and for weak force, the mediator or the particle that exchanges weak force, it's not really exchanging weak force, but that's responsible for this mechanism, are called W and Z bosons. And then there is the strong force that holds the nucleus together. Otherwise, the protons should be repelling each other and the nucleus should just like fly apart, right? Because the protons should be pushing each other away because they're all plus charges. But there is, prosaically called the strong force, and that holds them together. And that is mediated by gluon. So what didn't make sense in the early 60s was math. The math behind all this said that the photon and the bosons should all be massless. They should have no rest mass, zero rest mass. But experimentally, we found that Z and W bosons actually were very massive. They were like 80 or 90 times the mass of the proton. So this did not make sense. Why is this happening? And this is where Peter Higgs and Francois Englert and Robert Brock and other physicists came in to describe the mechanism that would allow for some particles to have mass and not others. So this is where they came up with what we now call the Higgs field. Higgs field is, well, you can also, there is a cricket ground at CERN that's called the Higgs field. So not to be confused with that cricket ground called Higgs field, but Higgs field is like gravitational field, magnetic field, right? So there is the Higgs field, and an excitation of the Higgs field is called the Higgs boson. So this is what they had done. They had like theoretically explained how some particles would have mass but not others, like how particles are getting mass by interacting with the Higgs field. And if the prediction is correct, then the Higgs boson would have to be found, and that is what took 50 years. So for 50 years, physicists searched for this particle, and then it was a big engineering project. The LHC took years, like decades, to build. The experiments around the LHC. I'm assuming people know the LHC. I didn't actually make any slide on the LHC. Now I think about it, the large collider. I don't know if you've seen it in news. It's like 27. It's just like a ring road, 100 meters underground, and then in there we strip protons from hydrogen molecule, ionize it, and then just push these protons around this ring until they are traveling almost at the speed of light, and then when they are like really, really fast traveling, we collide them at 4 points around the ring. So at Kolonki, at Gosala, at Sabdobato, and at Balaju. Exactly like that. And then as they collide, then we take pictures with what we call the detectors, right? So this is where the story stood at one point. So we knew how to explain everything, like electromagnetic force, the strong force, the weak force, and then there were these quarks and electrons that would make up matter. So everything we see around us are basically made up of up quark, down quark, and essentially electron. That should make up an atom. You take 2 up quark and 1 down quark, you have a proton, and you take 2 down quark, 1 up quark, you have a neutron, and then you throw in electrons, you have atoms, and you multiply by billions and billions, and then you have the universe. That's essentially the recipe for the universe, right? And there are these other exotic quarks, like these are heavier quarks. You make them in collisions of protons, you make them in labs, and there are these other heavier cousins of electrons. They are exactly like electrons, except they are more massive. And then there are, of course, the neutrinos. So this theoretical structure is called the Standard Model, and once we discovered the Higgs boson, this was supposed to be complete. So you could explain everything with this model. And we're like, okay, the work is done. Can we all go home now? We have the Standard Model. We can explain everything. But that's not the story. The story is there are just so many things that we don't understand. So the Standard Model is really good. Like, it's a good, beautiful mathematical theory. It makes many predictions. All of those predictions have been verified. We measure this particle, that particle, like all these particles have been found, including the Higgs boson. But there's just so much that we don't understand still. So, for example, the present theory says at the Big Bang, matter and antimatter were created in equal amount. But now, when we look around, all we see is matter. There is no antimatter. We don't understand why that's happening. So that's one of the problems that the Standard Model does not address. And there is the problem called neutrino oscillation. What that means is originally neutrino were supposed to be massless. They had like no mass. But experimentally, we find that it has non-zero mass. It actually has some mass and doesn't make sense. Why is that happening? We don't know. We have no idea. And there are many experiments that are trying to make sense of it, but we still don't know why that's the case. And the Standard Model, the theory that's supposed to explain everything, does not address that issue either. And there is this whole thing about dark matter. I don't know if you read news sometimes, like they talk about dark matter. The cosmologists, the astronomers, they look out in the sky, and then they tell us that there's just so much more matter, and we just don't see it. By see it, I mean not by just by eye, but by telescope, in infrared, in gamma ray, in any of the wavelength, we don't see it. We just know that it has to be there because of its gravitational effect. So you can tell there has to be some matter there. But we have no idea what that is, right? And there are...
Please excuse me, what's antimatter?
Antimatter is... have you seen Angels and Demons movie? Don't worry, I haven't either. But they talk about that there, and then they take it to a next level of evil. But antimatter is basically, let's say if you have an electron, E has a charge, negative charge, right? Anti-electron would be E with a plus charge. So everything else is the same. Its charge is opposite. So antiproton would be a proton, exactly like a proton but with a minus charge. And so when you take anti-electron and antiproton, throw them together, you have anti-hydrogen. So assuming you could do it forever, if it didn't destroy everything, you could do it forever, then you would have like antimatter on a larger scale, right?
It's not a massless quantity. They do have mass.
Yeah, they do have mass. Yeah, the mass is the same as the matter particle, so it would have the same. So at CERN there is one smaller experiment called, and it's just called antimatter factory, because they make some antiprotons and some antihydrogens, and that's very interesting actually. I don't even talk about it, but it's so fascinating. What they're doing is, all this gravity and all, you throw this, it goes down, right? You throw it and it goes down at 9.8 meter per second squared or something, and the experiment was testing if this happens for antimatter also. If you take antihydrogen and then just throw it, will it fall at the same rate? And I think they're finding it does. Isn't that fascinating? Even antimatter falls at the same rate. So yeah, so there is all these problems. So what we know, the whole thing I talked about, this standard model only constitutes about 5% of the matter energy content of the universe. All of this we don't know. This dark matter, this the dark energy, and so these are more than sufficient reasons to go and look for something beyond the present state of theory. So this works. Sorry. Okay. So when we go and tell theorists, and I'm sure in your field also you have theorists, you go and tell theorists, this is what we're seeing, we don't understand it. They always come up with like some new theory to explain your data, right? They're like, maybe if you do this, this will make sense. Maybe if you do that, maybe if you turn the plot upside down, it will make sense. These kind of speculations that theorists give you. But for us working in particle physics, we have classified all the theories, because theories give us like so many theories. To test them all out it's time consuming, right? It requires a lot of people, a lot of time. So we've basically divided them into two broad groups. One is called supersymmetry, everything else is called exotics. This is just management, right? The theories have different properties. So supersymmetry, what it says is just like antimatter. If you take an electron, flip its charge, everything else stays the same. Flip its charge, you get antimatter. What supersymmetry says is you take an electron, flip its spin. And by spin, what I mean is it's a very funny concept, the spin thing. It's a quantum physics concept. But for the sake of clarity, and don't quote me on this, I will use this analogy. Its spin is this. Let's say if the electron is not spinning like this, but if I were to do like this, that's my spin. Like, just like the Earth rotates around its axis. So think if you were to flip the spin of the electron, you would get a supersymmetric electron. That is the theory. So this has not been tested yet. We don't know if this is true. But this theory says if you flip the spin of all the particles that I showed in the previous slide, all the particles that you can see in this picture over here, if you flip their spin, flip is a very loose term, so don't quote me on this either. So I'm sacrificing a lot of technical accuracy for clarity. But if you flip the spin, then you get a whole new class of particles, and that is what supersymmetry says. But by doing that, it solves a lot of the problems of the standard model. It even provides a candidate for dark matter. It just comes out naturally in the theory. It says if you just do that, then you solve all this problem, and then you also solve the problem of dark matter. So it predicts a lot of new supersymmetric particles. Though for electron, it predicts selectron. For leptons, it predicts leptons, and supersymmetric. So they add S to everything. So quarks is squarks, and so forth. So they just add S, and so supersymmetry has its own language. And everything else is exotic. So in exotics, there are several independent models. Each model tries to address a particular problem. So for example, they would add, if we have extra dimension, if we had like one extra dimension, maybe we can solve this problem. Or if the Higgs boson that you just found, instead of being an elementary particle, maybe it is a composite particle, maybe it is made up of something else inside. If you assume that and do the maths, then you explain these few more things. And then in doing this, in both models, in extending the current standard model, they end up predicting new particles, and these are the new particles that we search for. And this plot is what we call the money plot. We show this to the funding agencies, and I did not know who was going to be in the audience, so I decided to put it here just in case we have somebody from STFC show up here. But yeah, what this plot does is, this is the latest plot. I think I took it 2 days ago. Oh no, this is from December 2017. Yeah. So what this shows is we have searched many places for supersymmetric particles. This shows, so for example, what this shows is this, the mass limits. If there is this particle, it has to be heavier than this. This is what this plot says. If this particle exists, it has to be in this phase space, not here. So we've looked in many different directions, and we have not found any new supersymmetric particle yet. So supersymmetric particles like the leptons and stop quarks and so forth, we have not found any of them yet. So we've been searching for this for a long time. So no new particle discovered yet. And this is another particle for the exotics that I mentioned. So there were 2 ways, right? And we've looked for quantum black holes. We've looked for extra dimensions. We've looked for, we've tested if or not there are additional heavier quarks. So instead of the 6 quarks that I've shown earlier, maybe there are other additional heavier quarks. None. We have not found any extra dimension, and we have not found any quantum black hole. We have not found any vector-like quark, like heavier quarks. So where do we go from here? We have a beautiful theory that works very well on a huge range. So I'm talking, this is recording me, this works fine, right? We can upload it on Facebook, that works fine. There's a lot of quantum physics there. There is a lot of special relativity, quantum mechanics, all these go into all of this. This works nicely, but we know there are some problems, and these problems are, for some people it's aesthetic problem. We have to have a theory that explains everything. There are these observations out there that we cannot explain. So there is that problem, but there is also scientific curiosity kind of problems. Like, we have to understand this, right? We are humans, we are smart people, we have to understand this. And so where do we go from here is the question. We've looked in so many directions, we have not found anything. Is it a dead end? Like, have we really come to the end of physics as we know it, or end of particle physics? But then there is some hope. There is some hope. And did you guys hear about the gravitational wave discovery? Back in 2016 or 15, there was this huge discovery. Einstein predicted it in like 1916 and 2016. Like, they finally announced the discovery of the gravitational wave. And there was this whole talk about this will now provide us a new telescope to study the universe, right? The Higgs boson is the same. It's not very different. The Higgs boson was predicted 50 years ago. We discovered it. Now we can use it to study further, right? To explore further, because we still have to measure its properties. For example, does it have the same spin as is predicted in the theory? Does it have the same decay mode? And by decay mode, I mean, does it decay into other particles like the theory predicts? And so these kind of things are still to be tested. And we've tested many of them. So when in 2012 the discovery was announced, the discovery didn't say, oh, we found the Higgs boson. It said, we found a particle that looks like the Higgs boson. That is how it was presented, because back then we did not know it was the Higgs boson that was predicted. We knew it looked like it and it behaved like it, but we had to characterize it properly to make sure that it was indeed the particle that was predicted. So since then, many properties have been measured. So we've measured its spin, we've measured its charge, which is 0. We've measured its different decay modes. They all match the predictions so far. But there is one property that's not been measured yet. So there is a property called, and this is the only equation I will show here. This property is basically, the name is not so important. It's called self-coupling, meaning how does the Higgs boson interact with itself? How does it give itself mass? That we don't know. I mean, there is prediction in the theory, and we're trying to measure. In this picture, what's happening is a Higgs boson going to 2 Higgs bosons, and we want to see or find out in the collision or collision that will have two Higgs bosons. So earlier, the discovery that was made in 2012 that had one Higgs boson when the protons collided, and we did it for a very, very, very long period of time, collected a lot of data, and then we found a few hundreds of events where one Higgs boson was produced. We would like an event, a collision, that will produce two Higgs bosons at the same time. And that is where this di-Higgs comes from. Remember Santosh Parazali, who did his thesis on di-Higgs? That is what he did. So he didn't do all of this. I mean, a lot of this is standard theory. What he did was he looked at data and then see if there is any di-Higgs event. If there is, so of course we didn't make any discovery because there is a lot of data that we need, because these events, I mean, to find a Higgs boson or single Higgs boson in the proton-proton collision at the Large Hadron Collider, we have to, it's like looking for a haystack in a needle in a haystack of needles. That's what it is like. So there's a lot of event that looks like the Higgs boson, the background, right? We all know signal and background. Well, many of us know signal and background, right? So the signal is very, very small rate, and we have to pick it up from a lot of background. Di-Higgs, or an event with two Higgs bosons, is still more rare, so we have to wait for a lot of data to make any statistically significant statement. And the current prediction or current calculation says we have to wait until 2040 to have enough data. So the Large Hadron Collider has to run for another 15 or 16 years before we collect enough data to say anything about the di-Higgs. So what can we do about it? So in the meantime, we can develop strategies on how to best do this when all the data becomes available. So remember when the Higgs boson was predicted in the 60s, and then they didn't find it in a few experiments for some time, but then they decided to build the Large Hadron Collider in the 80s. People were already starting to compute how we are going to find the Higgs boson once the data becomes available, right? So you run simulation, you do some sensitivity studies, some S over B type of studies to see how we can develop strategies to look for Higgs bosons. That is what we can already do, right? So anticipating, yeah.
How big this data can be?
A lot. So I mean, if we wrote everything down, we could not write all the collisions down because it's just a lot of data. So we do what is called filtering, let's say, or triggering. So protons collide, something interesting happens, and something interesting only happens only so often. And we're like, oh, does this collision have an overall energy of this? Then we write it to tape. Once we write it to tape, we decrease the rate from like 40 megahertz, I think, to 100 hertz or something. So it's a factor of 10 to the 5 or something reduction when it goes to the tape. And even after that, we collect maybe like hundreds of petabytes of data, like in 1 year. I think I'll be right with you. One estimate that I know this was true back in 2012 was if you wrote it all on DVDs and you stack it up, it's like larger than Mount Everest or higher than Mount Everest in 1 year. Yeah.
So all these data, like say, these are numbers that get measured by different sensors, or do they actually also e-measures? I have no idea how these experiments.
So ultimately, it's all voltage, right? Proton-proton collide. There's a lot of radiation, and the radiation are detected by either photomultiplier tubes, or there are like silicons, and there are calorimeters that will all convert into voltage, and then that can be made into image data, like the one that I showed in the first slide, that can be made into image data, or they can be read by writing scripts. Then you have some n-tuple format, for example, if you know n-tuple, right? Or a vector of data, let's say, right? And then you read it like this. So to do massive analysis, you do scripts and all, but to show plots to public, you make nice like image data, and then you say, this is what the Higgs boson look like. Yeah.
Yeah, but then when someone looks at these data, when you say, is it looking at the patterns in those data to look for whatever you're looking for to analyze? Is it mostly the patterns, identifying patterns on those, or you have certain models, different models you try to fit on those data?
Yeah. So it's both, right? So in some sense, it is identifying patterns because you know what some of the other events are like. because LHC has been running for 10 years, 11 years now. But before that, there was another accelerator outside Chicago in Fermilab where a lot of the experiments were done. So there is some calibration scale. And before not, but at the same time, the Fermilab was running. There was another lab in California, SLAC, and from there, some other particles were discovered there. And then we have like standard candles, so you can calibrate them. So in that sense, it is looking for those patterns so that we can calibrate the detectors at the Large Hadron Collider, right? Because we have, there has to be this event at this energy range. So you look for that pattern in some sense. The other part was, I forgot the second part. The patterns, and there was another thing, just analysis. Yes, and then there is the models, yeah. Yes, exactly. And then there are the models. There are models for the particles that are already found, so you run Monte Carlo simulation on them. And there are models for the not yet discovered particles, and then you have simulation for them. So you try to optimize your analysis so that you're sensitive to the new particle.
So it seems there are opportunities for machine learning.
Of course, I mean we use it all the time, like BDT and DNN. I think we were just discussing this earlier. So yeah, machine learning is a big name, like everywhere, but also in high energy physics, where we need a lot of pattern recognition and training. It's limited by the amount of data we can train on, but other than that, it's pretty cool. Yeah.
What is time frame like in the collider, like formation of Higgs particles or formation of dielectric and decay? So is the time frame big, or you can?
Yeah. So the collision rate like happens. So there's a bunch of protons that come and they collide every 25 nanoseconds, and in that, like there's like billions of protons colliding every 25 nanoseconds, right? In those collision, when the Higgs is formed, for example, it only lasts for so long. It only lasts for 10 to the minus 23 seconds or 10 to the minus 24. It's one of those. So immediately decays into something else. And that something else then interacts with the detector just like a camera. So in your camera, we have pixel detector, right? Chips, we have, what do you have? Silicon or something in the present cameras, right? And that silicon basically detects the light. It detects radiation, right? So just like that, we have a camera. When the Higgs decays into these other particles, and those particles are just radiations, they interact with the detector, and that's what we measure. And that happens 10 to the minus 23, 10 to the minus 24 seconds. As the lifetime is very short. Yeah.
I have a suggestion. Maybe while you're doing the Q&A, we can pull up a couple of videos that explains how the NFC works, because that would give you a more visual idea of the data collection and the events and how they're filtered.
We can certainly do that. I do have a video somewhere. Maybe we can come back to it like after the session, because talked about physics a lot. We can talk about Nepal a little bit, maybe like how this ties up with what we are doing in Nepal. I get too excited. Sorry.
Because you mentioned that you had the data collect until 2014, so I was just wondering, like, why until 2014?
Yeah. So that's a different question, right? So that question's got to do with how often can you make an event, a collide, that will produce two Higgs bosons, right? So that can be predicted in some models. You can say, well, you will make one every 3 months or so, right? And this is not the right number. So, but I'm just giving an example. One every three months. Then in 1 year, maybe you'll only have 4 events, right? And so if you collect it for 20 years, then you'll have 80 events or so, and then you can do some statistical analysis with this. This is not to be quoted directly. This is not exact numbers, but that's the idea. So the rate of production is very small, so you have to collect it for very long.
So is it not possible to accelerate that number of years?
Oh, exactly. That's what we're going to do in 2024. Even after doing that, it takes until 2040. So in 2024, so your question is basically, if you're colliding with 25 nanosecond, why don't you do like boom, 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 right? A lot at the same time, then it will be faster, right? That's more or less what we're going to do in 2024 or 25. It's called the high luminosity LHC. So instead of LHC, it will be HLLHC. So there is luminosity is higher, where by luminosity we mean the rate of collisions will be higher. So and there are technical challenges. So we could do it like infinitely faster, and then just in next year we can publish the paper with the dye Higgs, but we cannot do infinite technically.
It's not the problem of the detector not
it's not a problem of the detector, it is in the accelerator level, like how frequently can you collide them. Well, the detectors will also have problem, right, because the detector has some resolution, has some time resolution. It can only do so often, it can take pictures. Like your camera can only take so many pictures at a second, right? Cannot take infinitely many pictures like constantly. Somebody else had a question.
Yes. You mentioned something about quarks and supersymmetry. I was wondering, like Higgs, when you collide two Higgs, you have di-Higgs. I was wondering if there's something when you like collide two quarks, does it either form a new particle, or is there something called
Yeah, we are
quark
colliding two quarks all the time, right?
that
Well,
has a
it's
property
not
like
exactly. Sorry.
Higgs? The di-quarks that perhaps would have a property like a Higgs.
So when we collide protons together, we are effectively colliding quarks together, right? Because proton has quarks inside. Another proton also has quarks inside. So when this collision takes place, well, there are quarks and gluons inside a proton. So what happens is there is a term called quark-antiquark annihilation. So a quark in this proton and an antiquark in this proton, they collide, and then we get something else. So effectively, there is also gluon-gluon fusion, but there is also quark-antiquark collision to make this event. So when the Higgs or the other particles are created, there is effectively this collision going on. So Higgs collision is difficult, yeah, because Higgs only lives for 10 to the minus 23 or 10 to the minus 24 seconds, right? You have to make a Higgs collider would be more difficult, put it that way, to control it, because it does not have, it's more, protons are relatively stable, right? Protons, you just like take it from a hydrogen gas, right? From hydrogen gas, protons. Higgs, you have to collide these protons to get Higgs.
Sorry, I was wondering what's the model that you use to predict di-Higgs? Is it the same as the...
Yeah. So di-Higgs events are predicted in the standard model, the one that I discussed. It is also predicted in the standard model. So we can, so ultimately what we want to measure in 2040 is the standard model di-Higgs production, right? But since that's not accessible in present data because of statistics, there are other models that theorists will give us, say, oh, if you look for a graviton, or if you look for, these other new particles that will also decay into two Higgs, so you can at least have something to work with, right? So you have some model to work with based on which you can develop your strategies for anticipating the full data in 2040, right? So you work with those models. So there are models called Rendell-Sundrum gravitons that will decay into two Higgs, and then we work with those also in addition to the standard model.
Do you test their efficiency to predict di-Higgs as well?
So we do make efficiencies for all the models. So once they give us a signal, the theorists give us a signal, we do test what kind of efficiency we'll have, how many events we will see, and things like that. Yes, we do that. But we don't need that necessarily for the standard model di-Higgs, because there we know like what the prediction will be. So we look for that. Anything else in physics, or shall we move on?
So the particles that is generated by colliding, say protons or things, do these things also generate in natural events? Like, do they exist in nature by themselves, or you
Higgs.
always have to collide things to produce them?
So if they exist in nature by themselves, so we will need a detector to detect them, right? It would be difficult. You need the energy range, right? You need the energy. So I mean, I'm thinking maybe there are cosmic rays, and then there are so many cosmic rays and so many like rays coming. If it happens somewhere, right? We would not know of it because we would not have a detector to detect them, right?
But
So
it should be possible. Do you think that it is possible that they exist in nature, but we cannot detect it? Is that
to exclude the possibility is probably not very wise, because there's just so much radiation and these collisions happen, right? I mean, the cosmic rays that come to Earth that are coming are much more higher energy have much more higher energy than we can create in any lab, right? So there may be one has probably already done some calculation by making some approximations like there is so much rays coming, so, but it's probably possible. It would be good if we could build a detector up in the sky that we just detect it, then we would not have to spend billions of dollars making the LHC. Okay, where were we? So yeah, building models to do this and how this ties up with Nepal. So what Santosh had did was a master's thesis just looking for this Higgs boson pair production. This was probably the first master's thesis coming from Nepal, working with the LHC data and analyzing data because he got affiliation through ICTP, of course, but probably the first thesis done from Nepal. So what, right? Or as many of us would say in Nepal, kinapista, right? What literally translated is what have you measured, I guess, right? We measure the Higgs pair production, right? But yeah, so what, right? So you've done so. My personal opinion is that this is a fine example of how we can, for the future, look like already developed strategies. This is one example, but in today's seminar's context, or probably more importantly, how this can be done in Nepal. Like the student comes, like trains, learns the tools, goes back, and then through Skype supervision or emails, so forth, you can actually complete a project. So that's, if you can do it with master's thesis, I certainly see possibility with PhD thesis, for example, right? So it sets a good precedence, I think. And then we have to build up this collaboration. So right now, this was with the Atlas experiment, ICTP and TU, but in the future, maybe we don't even need ICTP. Maybe Nepal already builds a group has a group that can work on projects like this, and then we can partner on equal footing with the rest of the world. Like we'll be doing global scientific research in Nepal. So how are we going to get that done, right? So it's a long way. So my opinion is, 4 pillars of potential success. This may or may not be successful. We don't know. We just have to try it out. And my feeling is, these are the 4 pillars of potential success: education and training, public support, government support, and scientific R&D in Nepal, but also in partnership with the rest of the world. Because anything we do in Nepal, it has to have some global value, right? Which would then put us in a similar competition with the rest of the world. And that's the idea. So for education and training, we're already doing some of it, as I've discussed before. So we started these programs actually. Ab and I went to KU in December 2013, and we did an outreach program, a seminar, a discussion with students and faculty. And then they probably back then thought, oh, these guys, come from Europe, they give a talk, they will go, they will not show up again next year. But we were persistent. We basically went back every year after that, and now we have very good relationship with people in Nepal at KU and at TU, and we have collaborated on other projects ever since. So this is a picture I've already shown. This was in Sangha, this was in Sinduli, and this was a recent one. This was in December 2017. This was on the public day, Abba, right? I didn't go, so.
No, this was the first time we did an intensive school. It was a winter school. This is the first day of the winter school, and it was just for the master students, graduate students in Nepal from St. Xavier's, Golden Gate, TU, and KU. And it actually gave the students. So we took another Nepali physicist, a girl from Fermi Lab, Ajita Katiwala, and Kate Shaw with the ICTP, Jorg from CERN, and Mario from the college in London,
UCL.
UCL. And we did this physics school to actually give them training, but also to identify potential students who we could bring back for training and summer school programs.
Yeah. So this was an intensive winter school where Mario actually gave lectures, and then students were doing hands-on session later. And then there was a public day where the gender issue also was discussed, and that brought up some very interesting discussions in Nepal. As you can see, we went in 2013, 14, 15, 17. We didn't go in 16 because we had a choice between going to Nepal, doing outreach, or going to Spain and having a vacation. And so that's why we didn't go to Nepal in 2016, because we had an invitation from friends in Spain. But yeah, public support. How do we garner public support? So in all of these outreach programs that we've done, we always try to go and talk to the public. And by that, I mean like reaching out in high school, also in universities, doing colloquium at colleges or universities. And this picture is taken from December 2015 or January 2016. During that visit, we screened a movie called Particle Fever. Particle Fever is a movie made at CERN during the, well, not discovery, but following the LHC starting up to the discovery point. And it was a fascinating movie. So we did this screening, and there was just so much interest. Like, so many people showed up. There was a long list of people who wanted to come in but didn't find seats. And there was this is during the Q&A session after the movie. And so besides the movie, we also try to write these articles in magazines. Well, Ava does. She's the writer. So she writes these articles in magazines and newspapers. We've done some short episodes on NTV, I think, and then some other public events in college campuses. So this is just reaching out to public, because as scientists, we'd like to inform the people that this is the science we're doing, this is the importance of this science, so you have to support it. And the idea is, if the public supports it and the public, tells the leaders, then the leaders will have to support it. So, well, you would hope, if, the government will do, or the leaders will do what the public does, you would hope. But I guess it doesn't always happen. So besides the public support to do these kind of large-scale scientific projects, you also need support from the government. And I'm showing a couple of pictures. So whenever we have like dignitary visits in Geneva, we tell the embassy, please bring them over. We'd like to talk to them about science. And then here, I think this was the Minister of Health back then, who came, and we're showing him the CMS experiment, although he's busy taking a selfie. And then there's the ambassador. And this, we've received a lot of support from the mission in Geneva, actually. So because CERN is an international organization, the Geneva mission likes to keep good relation, and then and the ambassadors in the past two terms, I think both ambassadors have been very supportive of the initiatives, and then they've helped us a lot in establishing contacts in the ministries. And recently, actually, we signed, or the government of Nepal signed, an international cooperation agreement with CERN. What that means is now it allows, it provides a legal framework for scientists and students in Nepal to work on projects at CERN. So that's some good development. And now we're discussing with the Ministry of Science. I don't think Ministry of Science exists at this point in time, but something exists, I think, to force strategies for future collaboration. And here, I think the President visited CERN when she was here. She was very much supportive of CERN's mission, Science for Peace, because CERN was established post-World War II to bring together all the European scientists to work on a project together. And she liked that, and she also liked the fact that the practical spin-offs of particle physics, such as radiotherapy and radio imaging and so forth, because she herself is a cancer survivor. Apparently, I did not know that. So it's good. I mean, we don't need this, but it's good to have political support, right? It's good to have, because without political will, big projects are difficult to get done, right? You need the structure of the government. And so finally, R&D plus international collaboration. Besides the outreach program, we try to bring together scientists from CERN and from South Asia. There were 70 plus people overall who participated in this particular workshop held place in Dulikhel, Kathmandu University. The idea was to bring together scientists from South Asia region, and then to form sort of a cluster so that you can collaborate with CERN as one unit. So there is one interface between South Asia and CERN. So it has had some fruitful discussions, and a couple of good things came out of this. And one was there is a lot of goodwill among the scientists even in South Asia. So people from India would say, well, if you don't have this particular facility and you would like to test out your whatever, then you can come to our facility and use it. We just give you time. So there was this kind of, and there were people from Afghanistan who came and was like, we don't have enough teachers to teach courses in our university, and people from Nepal like, oh, we can come there and teach this for a semester or two. So there was this lot of goodwill among the people in the region. So that was one good thing that came out of it. And the other was basically, we had been talking about this for a while, but we basically submitted a formal proposal to CERN saying, can you help us build a high-performance computing facility at KU? Because one of the things we learned was the image data from the hospital are being deleted every 3 months. they have enough disk space to save text data, but all the mammograms and everything they delete it every 3 months. And here they would kill for that kind of data, right? Because you want to store your data, you want to do analysis on those data, but there they don't even have that. That's not the point. I mean, this space is pretty cheap. The idea is a large cluster where you can do massive analysis, not just for hospital clinical data, but also for seismology, for example, or environment, or massive simulation that the engineers have to run, which I learned is that they write their program, they collect their data, and you have to do massive analysis. What they do is they take it on, in tapes and go to Korea. And there they do the analysis, and then they take the results out and come back to Nepal, or they go to Arkansas where they have some collaboration. It's like, well, we can do it in Nepal, right? You don't have to. And they take it to Korea because the bandwidth is so low, right? The bottleneck is right there. So we're like, well, let's do it in Nepal. And then we submitted this proposal to CERN, and they're like, yeah, of course we can do it. Of course, these are not all new servers. These are retired servers. They are like 3 to 5 years old, but they are state of the art for Nepal. Like if you go and check out the facilities at Pulcho, I mean, I did this in 2015, and they were using stuff like that were already 10, 12 years old, right? And we're like, okay, this would be very nice. This is state of the art for Nepal. So the idea is to build a computing cluster in Kathmandu University, and then do research like this data analysis and so forth, but also do education and training for the students, and also for other faculty members from other universities. The other aspect of the R&D plus international collaboration is a work in progress. This slide is empty because I have nothing to say here. I want to do this. I want this done because I know the engineers in Nepal are like excellent. I mean, look at us, right? We graduated from Nepal, maybe high school or college, and then we made it out here, right, to Oxford or to CERN or to MIT. There are so many good people who come out of these schools. So much can be done. And if you think about it, some of them like stay in Nepal and work. We can bring them over here on secondment basis. So they are on tenure track, or they are already tenured. You bring them over, you apply for grants. You bring them over here to work on R&D. They come here for 3 months in a year, maybe over a period of 4 or 5 years, and then they go back, they train other students, but they continue to do that research with you. So it also, fosters this collaboration, but it actually is providing some deliverables. So you have a result. So this can be done. I'm thinking about this, but exactly how this will be done is something I need to work on. Well, all of us can work on, but this can be worked on, right? So all of this work that we've done wouldn't have been possible without many people. So we have to thank, of course, the organizers for letting me, ramble on for so long. But also many thanks to CERN, the LHC, Atlas CMS, and ICTP outreach programs. Many people there, Mission in Geneva, other government agencies in Nepal. Because you go to Nepal, you want to see somebody in the ministry, you have to wait in a long line, and I mean it's impossible to get to the secretary. But when people are supportive of your cause, and they know like you're not there for a personal reason, you're there for international collaboration, they're supportive of it. And so that was a big help. And many people, basically, I could not name them all. The list of people who should be thanked is as big as the list of Atlas authors, and that's already like 3,000, 4,000 people. I have not kept count. For example, this is the discovery of the Higgs paper. So this was in 2012 when it was submitted to PLB. I contributed to that paper. So I was over here. I was, I think, the 2,668th author on that paper. So that's how long. So I'm changing my name to A so that I will become the first author. So this goes by alphabetically. So this is what I think will happen in 2040. There'll be a big news headline in Kathmandu Post that Nepali researchers make a historical discovery. There is the Higgs, and there are 2 of these events because it's Higgs events. And I think this is possible if we build a critical mass in Nepal, train students, work with professors there and other scientists there. It's not impossible because we've already seen with the pilot project that this is possible. And this kind of basic science, I think, may or may not have any survival value. It may or may not have any spin-off, but it definitely adds value to our survival. And that's my personal opinion. And that's all. Thank you very much.